Hello everyone and welcome back to another video. Today we'll be taking a look at a very interesting problem. It's essentially the problem of creating some sort of algorithm to solve the game of Sudoku. And this is a really interesting problem. I'll be taking this particular board in mind, and just so we're clear on the notation, a zero represents an empty square, and obviously there's a number that represents that particular number square. And the place where I got this problem from is Project Euler, and it's question number 96 from Project Euler. Sorry, misspelled project, but I'm sure you get the gist. It's essentially project number 96, but essentially the question is, can you solve the game of Sudoku? And can you do this efficiently for a large number of Sudoku grids? And the initial way which I approached this problem is I essentially tried to solve it using deduction. So I'll just write it, tried deduction. And the way the deductive algorithm worked is for each cell, we would essentially classify cells based on their groups. And a certain group would be maybe a rows group, columns group, and this particular 9x9, 3x3 is also a group. And essentially we would start off with each particular cell having the possibility of any number from 1 to 9 inclusive. But then if there's a number inside the rest of the group which is the same as that number, then then we can eliminate that particular number as an option, right? And we would continue to do this for each cell and for each group. And this is essentially how we can solve this deductively, and this is how humans solve the game of Sudoku. And this puzzle is relatively straightforward, so this can be solved by deduction. But then, if any of you are like advanced Sudoku players, fortunately I'm not one of them, but if you are an advanced Sudoku player, then you know that not all games can just be solved by straightforward deduction. And even if they can, some of the deduction tactics can be quite tricky. So, for example, let's say hypothetically, if from our deduction we deduce that one of these two cells must be a 4, or let's say one of these cells must be a 6. I know that's not true in this particular case, but let's just say hypothetically that one of these cells must be a 6. Then one deduction tactic is saying that, okay, there's a 6 in this row, there must be a 6 in this row, since one of these two cells is 6. Therefore, the 6 in this particular row must belong to this particular cell. And it can't belong here, therefore this must be a 6. Tactics like this are very tricky for us to code, since, okay, this particular one shouldn't be too bad to code, but then there are various more, some of which maybe they haven't even been discovered yet. So it's actually not possible just to code a Sudoku solver just by deduction. So hence we need to think of a slightly better way to solve the game of Sudoku. So deduction doesn't really work, and it turns out that the correct algorithm to use to solve the game of Sudoku is backtracking. And backtracking is essentially it's a really neat programming technique, and it's used in all sorts of not only games but all sorts of algorithms. The first, I think the most famous case of backtracking is the n queens problem, which I'm sure if you Google it, it will come up. It's essentially if we have an 8x8 grid, we want to place 8 queens such that they don't attack each other on that particular grid. It's a really interesting problem, and the way we solve it efficiently is by using backtracking. And okay, I'll quickly just explain what backtracking does. So backtracking basically checks. It should be maybe. I'll just take a subset of the Sudoku grid, maybe something like this. So let's say if we were to solve Sudoku, instead we were placing the numbers 1, 2, 3, and 4 inside this 4x4 grid, and similar rules apply. So no two numbers in the same row, column, or group, where this is the group, can be the same. And let's say if this was the value, if these were all 1s, and maybe, actually, let's say these were 1s, and then this is a 1 as well. And we essentially want to use backtracking to solve the rest of the puzzle. Maybe let's say this is a 2, this is a 2 as well. Let's say this is a 3. This is something like this. Like I won't fill out everything, but I'm sure you get the idea. So if we were to use backtracking, then a naive solution would be we iterate over each cell and we see whether that cell can be a 1. Okay, so if we were to do that, we would have to iterate over effectively all 16 squares. Some of them are full already, so our job becomes easier. But we still have to iterate over 16 squares, check whether each of them is a 1. If it's a 1, then we move on, and then for each cell we essentially have a brute force solution, right? Because for each cell we're checking whether it can be each value. And this is really inefficient, as you can imagine, especially for a Sudoku grid, because the number of Sudoku puzzles are, I believe, around 10 to the power of 24. It's a very big number. I might be off by a few powers of 10, but it's too many to brute force. But then what backtracking says is that we don't need to check every single value for a 1. We can be smart about this. We know that there's not going to be a 1 anywhere here, inside this row. Likewise with this row, likewise with this row, likewise with this row. So that means that the only candidate move for a 1 would be in this particular cell. And now, okay, let's see how that works with 2's. So there's not going to be 2 anywhere here, here, or here. Or here as well. So that basically just leaves 2 candidate squares for a 2. One which is here, one which is here, and one which is here. Sorry, 3 candidate squares for a 2. So this basically means that rather than having to search through every single value for a 2, we only land on a couple of spaces for a 2. And if we essentially just extend this algorithm, this might not seem that simpler, but it is much simpler actually. I don't mean simple, sorry, I mean time efficient. It's much more time efficient than the brute force solution, because we're essentially narrowing down the possibilities on each leg of the traversal. So this is basically how the backtracking works, and this is how we will use it to solve this particular problem. Let's take a look at the code. Okay, the first one is just extracting the grids. That's specific to the problem, but what we're interested in is this backtracking algorithm. Now, before we go through that, I kind of glossed over some details earlier, which was the way in which we generate the groups. So some of the groups are easy to generate. If we go back to the whiteboard, I mentioned that the groups are essentially rows, columns, and these 3x3 squares. So it's easy to generate the rows and columns, but 3x3 squares we will need to come up with some sort of function for that, which is basically what our first function, which we'll be discussing, is. So we essentially just create smaller squares, and smaller squares are essentially, as the name suggests, a group of smaller squares. And these are essentially the 9 smaller squares which we have within the 9x9 grid. And we also have we have a function which essentially gets the square elements of that particular row and column value, because we're interested in for each row and column value, we're interested in all the groups which it's a part of. So essentially our squares, we create a global variable called smaller squares, and this smaller squares is the group of the 9x9 squares, as I just said. And if there's RC values within the square, then we return that particular square within the smaller squares. Okay, so that basically means that we can get the groups for the cell. And what this means is that this returns all possible groups for a certain row and column value. So we know that some of the groups are its rows, and the other ones is its columns, and then the final one would be the square elements for that particular row and column value. Okay, so these 3 functions were relatively easy, but now let's go through onto the hard function, which is the backtracking function. Now, what this backtracking function is basically what we discussed earlier. So we check for each particular cell. If it's a 0, first of all, then we essentially, if it's a 0, then that basically means that that particular cell is free, and if it's a 0, then we would essentially break. I'll come on to why we break. The reason why we break is because we're interested in, our backtracking algorithm wants to find the first row column value, which is free. So once it finds that, it should break, and that's the reason why we have this. So that's essentially what the first couple of lines is doing. All of these lines are just checking for the first particular value which is free. Now, if there's no value which is free, if row is still -1 after this iteration, then we know that we've basically finished. That's our base case for our recursion. Then we return the grid. Okay, now for the rest of it is, for groups, we get groups for self or row call. This is essentially just using this particular function. And now the rest of it is, first of all, we have the surrounding functions set. And now this surrounding numbers is basically each of the numbers which are in the groups. So this means that this is just so we're aware of which numbers we're not allowed to use. And now the numbers which we are allowed to use would be all the numbers from 1 to 10 which are not inside the surrounding numbers. The set of surrounding numbers is just the set is literally just the set of the numbers which are surrounding that particular number. And now for each number inside allowed, we essentially recursively implement this backtracking algorithm. So we create a copy of the grid and we assign that particular row column value to being that particular number. And then now that we've established that particular number as being a possibility, we recursively backtrack. And now it's not necessary that each of these backtracking grids would yield a valid solution. That makes sense, right? Because that would mean that if there were more than one solution, then that means that one Sudoku puzzle has more than one solution, which doesn't really make sense. So some of these will definitely return a none, and a none is basically when none is essentially if that grid isn't valid. Now, if it's not a none, then we return possibility, i.e. we return that particular grid. And essentially we'll let recursion handle the rest, and this will give us our final grid output. And now that's essentially the main Sudoku algorithm, but in case you're curious, for Project Euler question number 96, the way they've designed it, I'll quickly just maybe I'll just quickly show it. Okay, actually I can't really show it, but feel free to just open up on your browser in case you're curious. But the way they've organized the text file is it's essentially organized in several lines, and each line is a grid of the puzzle. So and we also would need to read the file name, and this part's just file handling, but it's essentially just a way of reading all the grids into one. I won't go over this in too much detail because that's not really the main part of this code. And then finally, we just need to test whether it works for the question. And what they asked for is to print the first 3 digits of each Sudoku grid and add them all up, which would give us our answer. So if we run our particular question for question number 96, then we should see our answer as being 24702, which is the correct answer for question number 96. So that's basically it for this particular video. I really hope you enjoyed watching. Hopefully you learned something new about how to solve Sudoku. Maybe you learned something new about backtracking. It's a really nice question, and thank you very much for watching. I hope to see you in another video next time. Bye.